Hi everyone. In this video, I'll be talking about doing some regression diagnostics, examining assumptions using SPSS. There are equivalent videos in SAS and R, just as a reminder. Uh, all the materials should be posted on Canvas as well. So for this, we're going to use baker.csv. I think it's called Baker EX 2013. The data, just as a reminder, we can look at the data briefly. The data are on They're simulated data based on a study looking at 200 children in a literacy program, and specifically our model. If we go back to here, we're looking to predict children's reading scores from child demographics, if a child is female and their age, mother's and father's level of education, their mother and father's age, and most importantly, because this was examining a literacy program, the mother's involvement in the literacy program and the father's involvement in the literacy program. So our first model here, we have our regression model. So the first bit, what I'm going to highlight here all the way down to method, that's the same as what we usually have in any SPSS regression code. And then we're adding on here this residuals command. So we're going to say residuals, and I'll ask for, to examine normality of the residuals, a histogram. Z-resid is standardized residuals. Outliers will highlight extreme cases based on residual scores, which is distance, leverage, and Cook's distance, which is a measure of influence. So it'll highlight specific cases. So if we highlight all this and run it, we have our results. So first results, so the usual SPSS results, the variables entered, removed, model summary R squared, our overall model ANOVA, regression slopes with betas and all the other fun stuff. And you can obviously add this on to anything else you'd want. If you fit multiple regression models in the same command, and you're looking at change in R squared, you're going to get residual statistics for all of them separately. You could also add on things like semi-partial R squared and all that other fun stuff. Here, residual statistics, this gives you general information on the residual statistics. So the first is the predicted value, the standardized predicted value, the standard error of that, adjusted predicted values, residuals, standardized and studentized residuals, studentized deleted residuals down here, which we've all talked about, Mahalanobis distance, Cook's distance, and leverage. And so these are just overall values. They're not super useful. I mean, they're a little bit useful in that you could look at, if you wanted to, as a quick scan, like the standardized, the studentized deleted residuals, again, values greater than 2 or 3 are ones we'd want to consider, and we can see some of those. And then this outlier statistics, this highlights potential extreme cases. So we're highlighting the 10 most extreme cases on standardized residuals, on Cook's distance, and on the leverage. So case number is the row number, statistic is the value of that statistic, and then a significant F I would ignore. This is not really something we want to do significance tests on. We've defined this based on other general cutoffs. So again, this gives you cases to examine. So the largest residual was case 169, negative 2.75. And this is the absolute value. So you can see the largest, negative 2.75. There's another that's 2.470. I might consider those, again, these are cases to keep an eye on, 169, 121. If we look at Cook's distance, which is again a measure of influence, we can see what cases have the most influence. 169 is up there. It has a lot of influence as well. And then leverage is about the predictors. As a reminder, we can see what cases have the highest leverage. And again, we want to consider leverage, which would be 2k minus 1 over n. So in this case, there are 1, 2, 3, 4, 5, 6, 7, 8 predictors. So 8 minus 1 is 7, 14. So 14 over 200, which would be anything over about 0.1 or 0.9 is something you want to look at. So case 116 and 132 and 32 in terms of leverage. Again, we might see if they pop up somewhere up here as well to examine those cases. If we want to examine normality of residuals, one way to do it is a histogram here with a normal distribution. That looks pretty normal. It's pretty bell-shaped. It's not perfect, but it's pretty bell-shaped. We can also look at these things So we can also look at, remember in terms of assumptions, this residual plot. So this will give us the same part up here, down here under scatter plot. It will give us a plot. We're going to plot standardized residuals by standardized predictor value. This is one of the plots we talked about in lecture. And I'll scroll to the bottom to look at the plot. And we would expect that if there's a straight line here, we would expect that all these points follow this straight line and are pretty equally distributed among them. In this case, that looks pretty good. That's not really something we'd be terribly concerned about. If we wanted, instead of a histogram, we wanted a QQ plot, what we can do that. So we can run the regression. And what we're going to do is, it says save here Z resid. We're going to save the residuals as a variable. So if I run this model, by default, SPSS will give you a PP plot, which is based on probabilities, not quantiles. It's not quite as useful as a QQ plot. So you can look at this, or what we can do is if we look back at the data now, in the data, there's another variable at the end that wasn't there called ZRE1. These are Z-scored for the residuals for the first model we fit. It was automatically put in our syntax with this save resid. And then we can use, there's a function called ppplot we're going to use for QQ-plot. We're going to do this for the variable, and we can get a, down here, a QQ plot of the residuals. And again, everything follows on the line. Our residuals look pretty normal. This is looking pretty good. This is about what we would expect if those assumptions are made. The last thing, if we want collinearity diagnostics, I add up here under statistics. So statistics, we're estimating coefficient, Out's confidence interval, R, the overall ANOVA, R squared change, and then we add colon and tol. And this will give us collinearity diagnostics and tolerance. So if we run this, I'm going to come back to the coefficients in a moment. Down here, there's this collinearity diagnostics table. This is honestly not useful. It's not something I usually pay attention to. Instead, we talked about both tolerance and VIF as measures of collinearity, or VIFs over 10 and tolerance over below 0.1. Remember, they're just inverses of each other. And so for each factor, we have all of those. If you want other things in SPSS, things like DF betas and things like that, you can get them, you can request them. Usually what we, with those, I'm not sure they're available on the outliers, but you may be, but for DF betas, you can, the save option, you can save DF betas and other regression quantities as well. So thanks for listening. If you're curious, check out the SAS and R versions.